Reach out right now and press your fingers against the nearest surface. Feel that resistance, that unmistakable sense of solid stopping solid. What if I told you that sensation is a lie? Your nervous system tells you 100 times a second that in the truest physical sense, your hand has never touched anything in your entire life. Not the table in front of you, not the ground beneath your feet, not another person's skin. Somewhere between the atoms of your fingertip and the atoms of the world, there is a gap that has never once closed. And yet, you feel it close. So what exactly is happening in that space where nothing is supposed to be touching, but everything feels like it is? We grow up trusting our hands completely. A wall is hard. A stone is solid. When you knock on wood, something in you insists that two objects have made contact. Boundary against boundary, matter against matter. It's one of the most basic truths we build our entire understanding of reality on. Push a book across a desk and it slides because it's resting on something solid beneath it. Clap your hands and the sound you hear is proof. Surely that skin has met skin. Every physical interaction in your life, walking, eating, embracing someone you love, seems to depend on this one simple idea, that solid things can touch other solid things directly. But the deeper physics goes, the stranger this certainty becomes. Because atoms, the building blocks of your hand and the desk and the wood and the stone, are almost entirely empty space. If you could inflate a single atom to the size of a football stadium, its nucleus would be smaller than a grain of sand at the 50-yard line. Everything else, everything that gives your hand its apparent solidity, is just a haze of electrons smeared across that emptiness like fog. So if atoms are mostly nothing, why does nothing feel like something? To understand what's really happening, we first have to understand why atoms don't already collapse. Picture an electron orbiting a nucleus, the way old textbooks like to draw it, a tiny charged particle circling a positively charged core, like a planet around a sun. Classical physics, the physics of Newton and Maxwell, makes a very specific prediction about this picture. And that prediction is catastrophic. An orbiting charged particle should constantly radiate energy. And as it loses energy, its orbit should shrink, not slowly. Almost instantly, in a fraction of a second, that electron should spiral directly into the nucleus, and the atom should implode. According to the laws that govern falling apples and orbiting planets, matter itself should not exist. Every atom in the universe, every star, every living thing should have collapsed into nothing almost the moment it formed. Obviously, that isn't what happens. So something else, something deeper than classical physics, must be holding reality together. That something is the strange, counterintuitive world of quantum mechanics. At the heart of it lies the Heisenberg uncertainty principle, one of the most profound discoveries in the history of science. It tells us that a particle's position and its momentum can never both be perfectly known or perfectly fixed at the same time. Try to trap an electron in a smaller and smaller space near the nucleus, and its momentum, its raw kinetic energy, is forced to grow larger and larger in response. Almost as if the universe refuses to let anything be truly pinned down. This isn't a failure of measurement. It's a fundamental feature of reality. And it means that squeezing an electron down to nothing costs an infinite amount of energy. That resistance is what stops the atom from collapsing. It stabilizes a single atom at a very specific, very stubborn size. But here's where the story gets more interesting and far less obvious. The uncertainty principle explains why one atom holds its shape. It does not explain why an entire universe of atoms, trillions upon trillions of them, doesn't simply crush together into an unimaginably dense point the moment they get close. Why does bringing two objects together release almost no energy at all, instead of an explosive burst that would make every physical contact in the universe act like a bomb? For decades, this question sat quietly at the edge of physics, until 1967, when the physicist Freeman Dyson, working with Andrew Leonard, proved something remarkable using pure mathematics. They showed that ordinary matter is stable not just atom by atom, but in bulk, in stars, in stones, in your own bones, because of a single, almost bureaucratic-sounding rule of the quantum world, the Pauli exclusion principle. Electrons, it turns out, are deeply antisocial particles. No two of them, in the same system, are ever permitted to occupy an identical quantum state. Later, in 1975, physicists Elliot Leib and Walter Tyrring found an elegant shortcut to the same proof, revealing just how directly this exclusion principle enforces distance between particles of matter. Without it, without this strange cosmic rule against sameness, gravity and electric attraction would pull all matter into runaway collapse. The universe, quite literally, is only stable because electrons refuse to share space. And this is where the illusion of touch begins to unravel. Because atoms don't have edges. They don't have shells, or surfaces, or boundaries in the way a marble does. Each atom is a fuzzy, shifting cloud of probability, a ghost of where an electron might be found, blurring outward with no sharp end. When you bring your hand toward a table, you are not bringing solid boundary toward solid boundary. You are bringing one electron cloud toward another. As the distance closes, those clouds begin to overlap, blending into each other's territory. And it's here, in that overlap, that the exclusion principle activates in full force. The electrons in your fingertip and the electrons on the table's surface are suddenly being asked to occupy the same region of space. But that is precisely what is forbidden. Long before your finger's atoms could ever physically merge with the table's atoms, this quantum law throws up a wall, not a wall of solid matter, but a wall of pure prohibition. This resistance has a name, Pauli repulsion, sometimes called exchange repulsion, and it is almost unimaginably powerful at short range. Two separate mechanisms conspire to produce it. First, when overlapping electron wave functions are forced to stay distinct from one another, they twist and bend to avoid overlapping states. And this distortion sharply increases their curvature, which in quantum terms means a sudden, violent surge in kinetic energy. Second, because same-spin electrons are forced apart from each other, a strange kind of empty pocket opens up between the two approaching surfaces, a thinning of the electron fog that would normally shield the positively charged nuclei from one another. With that shielding stripped away, the nuclei feel each other's raw positive charge directly, and they repel each other with tremendous force. Two invisible mechanisms, one from the quantum geometry of electrons, one from exposed electric charge, combine into a single, formidable barrier. That barrier is what you feel every time you believe you are touching something. Here is the part that should genuinely unsettle you. That barrier operates across a gap. A real, physical gap, just a few angstroms wide, a distance so small it's almost meaningless to imagine. And yet it never fully closes. What happens next is not a story about physics alone, but about biology translating physics into experience. Your skin is embedded with extraordinarily sensitive mechanoreceptors, specialized proteins like piezo2 and elkin-1 that respond not to contact, but to force. When the electron clouds of your fingertip press against the electron clouds of the table, the resulting repulsion pushes back against your skin with real, measurable force, deforming the tissue at a microscopic level. That deformation stretches the membranes of these mechanosensitive channels, physically prying them open, allowing charged ions to rush into your nerve cells. That rush of ions creates an electrical signal, which races along your nerves to your brain, where it is finally translated into the unmistakable, convincing sensation of contact. Every single time you have ever felt something solid, your brain was not reporting physical contact. It was reporting the outcome of a battle between electron clouds that never once collided. If this is true here, in the gentle world of hands and tables, what happens where the stakes are higher, where nature is not gentle at all? Deep inside the core of a star, gravity applies pressure so extreme that atoms are stripped down to bare, naked nuclei, stripped of their electron clouds entirely. Even then, two positively charged nuclei should repel each other far too strongly to ever get close. And yet, stars shine. They do it through a loophole in reality itself called quantum tunneling nuclei, borrowing just enough quantum uncertainty to occasionally appear on the other side of a barrier they should never be able to cross. A probability precisely described by something physicists call the gamma factor. Once close enough, within femtometers, an entirely different, overwhelmingly powerful force, the strong nuclear force, seizes them and fuses them together, releasing the light that has crossed the universe to reach your eyes tonight. And when stars die, the same exclusion principle that stops your hand from falling through a table becomes the only thing standing between a dead star and total oblivion. In a white dwarf, gravity is held at bay purely by electron degeneracy pressure, the same refusal of electrons to share identical states, now straining under the crushing weight of an entire collapsed star. But push past a very specific threshold, the Chandrasekhar limit, near 1.5 times the mass of our Sun, and even this resistance fails. Electrons are forced to merge with protons, transforming into neutrons in a catastrophic implosion. The collapse doesn't stop until an even deeper form of quantum resistance takes hold: neutron degeneracy, reinforced by the raw, repulsive core of the strong force itself, freezing the collapse into the densest material object known to exist in the universe. A neutron star, a city-sized sphere containing the mass of a sun. So the same invisible law that lets you rest your hand on a table without falling through it is the very law that determines the fate of dying stars. The very thing you interpret as the simplest, most obvious fact of your physical existence, solidity, contact, touch, is actually one of the deepest and strangest results in all of physics. A law written into the fabric of reality that governs everything from a fingertip on a countertop to the death throes of a sun. We are not made of solid matter, bumping into other solid matter. We are made of quantum fields, held apart by a rule with no classical explanation, translated by biology into a feeling so convincing that humanity spent its entire history believing something false about the most basic act imaginable. Perhaps that is the quiet, profound truth hiding underneath everything you touch. You have spent your whole life inside a universe where nothing has ever truly met anything else, and somehow, out of that eternal, unbroken distance, reality still manages to feel whole.